So look at this slide. The title say it all, dust load calculation. So this protects the downstream equipment. Why is that so important? Because blast furnace top gas is not clean. It carries a lot of dust. If you don't calculate the dust load correctly, three bad things happens. What are that? So the first is the scrubber will choke. It fill the mud and the stop cleaning gases. The second is the fan eroded. The dust particle act like a sandpaper on the fan blade. And third, the stove clogs. The dust build up in the checkers, reducing heating efficiency. So getting dust load right is not a theoretical exercise. It's about keeping your furnace running without an unplanned stop. So remember the bottom line. A wrong dust load is equal to trouble. Coming to our further course of action forward. So now let's look at the three key parameters you must know before any dust load calculation. First, hot metal production, example 6000 TPD. The more iron you make, the more gas flows and the more dust you carry. So second, productivity in tons per cubic meter per day. So typically range of 2.2 to 2.8, and here is a critical rule. Higher productivity means more dust. Why? Because you push the furnace harder. Gas velocity increases, the fine particle get carried out instead of settling. So third is the top gas volume in the normal cubic meter per ton of hot metal. So typically 1400 to 1700 normal meter cube per ton hot metal. From these three, we calculate total gas flow, the backbone of everything. Formula is the gas flow normal meter cube per hour as it's shown is equal to hot metal production into top gas volume divided by 24. So look at the small table at the bottom. At low productivity 2.0, dust concentration is about 15 gram per normal meter cube. At high productivity 3.0, it jumps to 25 to 30 gram normal meter cube. So that is almost double. So always adjust your dust load to productivity. Never assume a fixed number. So coming to the our primary dust catcher. So if we come across the primary dust catcher, we can see that it's basically deal with the coarse dust load. So if we come across the calculation, this slide shows the step-by-step calculation for the primary dust catcher. So usually a gravity settling chamber or a simple cyclone calculate the total dust entering the primary catcher, and total dust kg per hour is equal to gas flow normal meter cube per hour into raw gas dust concentration, that is gram per normal meter cube, divided by 1000 to get kg per hour. So typically raw gas dust for a high productivity blast furnace is 20 to 40 gram per normal meter cube. So coming to the next step about knowing the removal efficiency of the primary dust catcher. So for particle larger than 50 micron, it's about 55 to 65%. It will not catch fine dust. As for the moving forward, calculate dust leaving the primary dust catcher. This goes to the secondary unit. Outlet dust is equal to inlet dust into 1 minus efficiency. So let's run the example given. Gas flow is equal to almost 400,000 normal meter cube R minus inlet dust is equal to 30 gram per normal meter cube. So that gives a inlet dust rate is equal to 12,000 kg per hour, where the primary removes 60%. So outlet dust is equal to 4,800 kg per hour. So one important design tip: if you increase productivity, you must increase primary catcher diameter or add parallel cycle on. Otherwise, the gas velocity becomes too high for the gravity settling and efficiency drop. So coming to our dust removal efficiency part, about a secondary cyclone, where we compare the uh, next two stages, that is secondary dust catcher cyclone and wet scrubber. So look at the images on the side. By side you see a cyclone body on the left and a scrubber on the right. Secondary cyclone, it removes the dust that escape the primary catcher, and mainly particle between 10 to 50 micron efficiency, that is 70 to 85%. So for example, if 4800 kg per hour entering the cyclone and efficiency is 75%, then only 1200 kg per hour goes out to the scrubber, so wet scrubber, and this catches the finest dust, submicron particle. We can say efficiency is around 90 to 90%, and in our example 1200 kg per hour entering a scrubber efficiency 90% or 95% even. So final dust leaving to a clean gas main is only 60 kg per hour. So important note on the slide is the higher productivity increases the primary catcher diameter or add parallel cyclone. That sentence is repeated because it is critical. Do not try to fix a high dust load by overloading the secondary cyclone. So this is what is the gist. So also remember the scrubber is designed for the dust load, leaving the secondary, not the raw gas. So if you skip that, your scrubber will be undersized. So coming to the blast furnace uh, gas cleaning flow. So dust reduction chain and design tips we will share in this slide. So this is the complete gas cleaning flow from furnace top to the clean gas main. The image shows the chain. Blast furnace top gas goes to primary dust catcher, then secondary cyclone, wet scrubber and clean gas to stoves, power plant or TRT, whatever. So each step reduces the mm, uh, dust content. So each reduction is significant. So as far the primary is concerned, it removes coarse dust more than 50 micron, about 60% of the total mass. Secondary removes medium dust 10 to 50 micron, another 30%. And a scrubber removes the submicron, that is 8 to 10% of original. So why do we need all three? Because no single device can do the whole job. Gravity setters fail on the fine dust, cyclone fail on the submicron dust. Scrubber are the expensive and high pressure drop. So you only send the remaining fine dust to them. Now the design tips on the slide 1. If final dust more than allowed limit, say above 50 milligram per normal meter cube for the stove, you must increase the scrubber delta P pressure drop or add a two-stage scrubber. If cyclone overloaded, meaning you see the dust carry over into the scrubber, you must increase the number of cyclone in parallel, not just make one bigger. Parallel cyclone reduces gas velocity per cyclone and improve efficiency. So final rule for team is always calculate dust load step by step, production gas volume, primary outlet, secondary outlet, scrubber outlet. Never jump directly to the scrubber sizing. Any question on these 5 slides? If it is there, you can share, and let us concentrate with all this data and statistics and monitor our dust load as per the design and according